All right, writing and using recursive and explicit rules for arithmetic sequences. So remember that an arithmetic sequence is a sequence in which there's a common difference between each term in the sequence. What that means is you're always adding by the same amount. For example, in this sequence here, you can see that in order to get from one term to the next term, you're adding 1,000 each time. Okay, that's the common difference. Now your common difference could be a fraction, it could be a decimal, it could be a whole number, and it could be a negative number. And so the common difference is represented by the variable d for common difference. Okay, so whenever you have a common difference, you have an arithmetic sequence, and we can write recursive and explicit rules to explain or to represent that sequence. So in order to write a recursive or explicit rule, you need two pieces of information. The first piece of information you need is f of 1, which is the first term. For example, in this case, our first term is 5,000. I'm going to write that down here. And you need the common difference, which I already mentioned to you. And we can see in this sequence, the common difference is we're adding 1,000. So I'm going to put here plus 1,000. So both of these rules, the recursive rule and the explicit rule, have parts that always look the same. And then all you got to know is what to change. Okay? So in a recursive rule, most of the rule is always going to look the same. And I'll write that piece in black. So we have here f of n equals f of n minus 1. Remember, f of n minus 1 just means the previous term. Now the only part that changes is the end, plus d. And that part is specific to the specific sequence you're dealing with. So in this case, for this sequence, our recursive rule looks like this. F of n equals f of n minus 1. And what is my common difference? Plus 1,000. And there's the rule. It's that simple. Now, whenever you're using a recursive rule, you always have to identify the first term. So we're going to say, okay, f of 1 equals 5,000. And that's your recursive rule. Now, usually what you'll see is they'll say for n is greater than or equal to 2. Now, why do we say that? Well, when you give a recursive rule, when you write a recursive rule, you give the first term. So when do you start using the rule? You start using the rule at the second term. So that's why we write for n is greater than or equal to 2. So let's take a look at the explicit rule. Same thing. There are parts of the explicit rule that do not change. And so those parts are in the front and in the back. So explicit rule, we always have f of n equals. I'm going to skip a space here and I'm going to put in the back end here in parentheses n minus 1. Okay? And we're going to put the same pieces. These two same pieces are going to fit in here. You have f of n equals f of 1 plus d. Now you're not actually going to write f of 1. You're going to write first term there. And you're not going to write d. You're going to write whatever the common difference is. So then very easily I can write my explicit rule is f of n equals my first term, which is 5,000, plus my common difference, which is 1,000, times n minus 1. And there's my explicit rule. Now, why the n minus 1? Well, if you notice, in the explicit rule, the first thing I give is the first term. So I'm trying to find the rest of the terms, and so n represents all the terms, including the first term. But if I've already given the first term, how do I exclude that from this multiplying by 1,000? Well, I do n minus 1. So this minus 1 here is excluding the first term, which we've already given. All right, let's go ahead and move on to our second example here. These should move quicker because I've already explained the basics. So this table shows the number of plates left at a buffet in n hours. Write a recursive rule and an explicit rule for the arithmetic sequence represented by the table. So we have here 155, 141, 127, 113, 99. So what is my first term? What's f of 1? It is 155. And what is the common difference? Well, you can see here that we're actually subtracting or adding negative 14. So that's my common difference. All right, so let's go ahead and write our recursive rule. Again, all of this stays the same. F of n equals f of n minus 1. And the only thing that changes is d at the end. So I could write, since this is a negative 14, I could write plus negative 14. But adding a negative and subtracting are the same thing. So I could simplify this and I could just write minus 14. So that's what I'm going to do. Again, when we're writing a recursive rule, we need to identify the first term. So we say f of 1 equals 155. Okay? Now our recursive rule, not recursive, sorry, explicit rule. Again, the front is going to be f of n equals, and in the back we're going to have n minus 1 in parentheses. And all we're going to stick in the middle is first term plus the common difference. So my first term is 155 plus negative 14, or just simply minus 14. And there is our explicit rule. All right, next example. We see here we have a graph, number of hats over time. Jerry collects hats. The total number of hats in Jerry's collection depends on how many years he has been collecting hats. After the first year, Jerry had 10 hats. Each year, he has added the same number of hats to his collection. The graph shows a sequence. Write an explicit rule in function notation for the arithmetic sequence. So this time, we only need to write the explicit rule. So some of you might be able to see what's going on from the graph, and some of you would benefit from actually making a table. So let's just go ahead and make the table real quick. I'll do it right here. All right, so I'm going to put here n and f of n. And remember, our n, that's our input, so that's going to be our x values, and our f of n, that's our output, that's our y values. So we have here 1, 2, 3, 4, and our y values, or our output values, 10, 18, 26, 34. 10, 18, 26, 34. And so we need to identify our first term. In this case, that's going to be 10. And what's our common difference? We can see here that we are adding 8 for each new term. So that's going to be our common difference. It's going to be plus 8. And this time we only need to write the explicit rule. So that's going to be f of n equals, let's do this in order now. First term, 10, plus our common difference, 8, times n minus 1. And there is our explicit rule for this data coming from this graph. All right, a few more examples here. Scroll to the top. Here we go. Now, in these, we're actually going to write an explicit rule and use that explicit rule to find another value that's not represented by the table. So if we look here, suppose the table shows the cost in dollars of postage per ounce of a letter. Determine the value of f of 9 and tell what it represents in this situation. So let's think about f of 9. If f of 9, n is the terms, right? So that would be the 9th term, but what does it mean in the context of this problem? Well, it's the number of ounces, so it's how much the postage weighs, okay? And f of n, that is going to be the cost of the postage. So let's take a look at our values, the same as we've been doing before. What is my first term? F of 1, that's going to be 0.35 or 35 cents. And what is my common difference? If I look here, 0.35 to 0.55 to 0.75, I can see that my common difference, we are adding 0.2 or 0.20. So what are we going to do? The same thing we did before. We're going to write our explicit rule. So f of n equals first term, 0.35, plus my common difference times n minus 1. And now here you're going to see how the n minus 1 works. Okay, so now I want to see, well, what's f of 9? So we're going to say f of 9 equals 0.35 plus 0.20 times, remember, if we're saying f of 9, that means n is 9. So this becomes now 9 minus 1. And what's 9 minus 1? It's 8. So now we have f of 9 equals 0.35 plus 0.20 times 8. We just follow PEMDAS here, we multiply. So 0.20 times 8 is 1.60 plus 0.35, that is 1.95. So f of 9 is 1.95. In other words, in the context of this problem, a 9-ounce letter is going to cost $1.95 in postage. And notice what happened here, because this is always going to happen. Notice that we had f of 9, and this number was 8. Remember, think about n minus 1. So if you understand what's going on here, the number back here in this parentheses is always going to be 1 less than the number here. Next example, same concept, except we're getting our information from a table. DeAndre collects feather pens. The graph shows the number of feather pens DeAndre has collected over time in weeks. According to this pattern, how many feather pens will DeAndre have collected in 12 weeks? So, again, we can look here at our graph and turn that into a table if we need that kind of help to visualize what's going on here. All right, so we have n and we have f of n, 1, 2, 3, 4 for the 4 weeks, then 18, 37, 56, 75. 18, 37, 56, and 75. And we can identify our first term is 18. And what is our common difference? Well, if this was 38, right, then our common difference would be 20, but it's 1 less, so our common difference is we're adding 19. So now we can find out what's happening in week 12 by writing our function. So f of n equals our first term, 18, plus our common difference, 19, times n minus 1. All right, so now we're going to plug in for f of 12. So f of 12 equals 18 plus 19 times. So if n is 12, what's going to be 12 minus 1? 11. Okay, so then we work this out. And we have 19 times 11, that's 209. Plus 18, that's 227. So f of 12 equals 227. So again, what does that mean? That means after 12 weeks of collecting feather pens, DeAndre should have 227 feather pens. All right, last example. In this example, you can see that there's no table, there's no graph. There's just some words and some numbers. So let's take a look at it. The odometer on a car reads 34,240 miles on day 1. Every day the car is driven 57 miles. If this pattern continues, what will the odometer read on day 15? So you might think, wait, without a table, without a graph, how am I going to find F1 and how am I going to find the common difference? Well, they actually give it to you right here in the question. They tell you the odometer on a car reads 34,240 on day 1. Okay, well, that's my first term. Day 1, 34,240. And then it says every day the car is driven 57 miles. So if the car is driven 57 miles every day, that means every day we're going to add 57 more miles. So that's my common difference, is plus 57. So let's go ahead and write our explicit rule. We have f of n equals my first term, 34,240, plus my common difference, which is 57, times n minus 1. And we want to find out what it's going to be like on day 15. So f of 15 equals 34,240 plus 57 times, again, if n is 15, what's n minus 1? It's 14. And so we work this out. So 57 times 14 equals 798. And 798 plus 34,240 equals 35,038. So on day 15, the odometer on the car should read 35,038.